Hello again. Today we will answer the advanced study assignment for experiment number 14, heat effects and calorimetry. Just a reminder, the advanced study assignment calculations are similar to the lab report calculations. In this particular case, question number 1 is the calculations for part A of the experiment titled specific heat, and question number 2 is the calculations for part B, heat of solution. Part C will include calculation from both question 1 and 2. So let's start with question number 1. Question number 1 has several parts to it, where we will finally at the end of the question be able to calculate the specific heat of an unknown metal and approximate its molar mass. The question states a metal sample weighing 147.90 grams and at a temperature of 99.5 degrees Celsius was placed in 49.73 grams of water and a calorimeter at 23.0 degrees Celsius. At equilibrium, the temperature of the water and the metal was 41.8 degrees Celsius. And the first part of the question, part A, says, what was delta T of the water? And it gives us the formula. Delta T, which is change in temperature, is always the final temperature minus the initial temperature. So here it seems that we have a very hot metal that was sitting in boiling water for some time. That's how its temperature came to become 99.5 degrees Celsius, because that's very close to 100 degrees Celsius, the boiling temperature of water. It was placed in almost 50 grams of water, 49.73 grams of water to be exact, at room temperature at 23.0 degrees Celsius. After a while, the equilibrium temperature of both the water and the metal was 41.8 degrees Celsius. So here it seems that all of the thermal energy, or the heat energy of the metal, was transferred from the metal into the water. And that raised the temperature of water from 23.0 degrees Celsius to 41.8 degrees Celsius. So to calculate the change in temperature, we will take the final temperature minus the initial. So here, delta T of water will equal 41.8 degrees Celsius. That's the equilibrium temperature for both the metal and the water, minus the initial temperature of water, which was room temperature, 23.0 degrees Celsius. With change in temperature, you have to be careful with the positive and negative signs. So here, this is a positive change of 18.8 degrees Celsius. So our answer is positive 18.8 degrees Celsius. So part B of the question says, what was delta T for the metal? And we will use the same equation for delta T as we did in part A. Delta T is the final temperature minus the initial temperature. But this time we'll use it for the metal, not for water. So if we look, the initial temperature of the metal was 99.5 degrees Celsius. And the final temperature was the equilibrium temperature, 41.8 degrees Celsius. Okay, so to calculate the delta T for the metal, we will say delta T, and this is going to be for the metal, will equal final temperature minus the initial temperature, which will equal final temperature is the equilibrium temperature, 41.8 degrees Celsius, minus the initial. The metal started at 99.5 degrees Celsius. So here, if we look, we have to, again, like I said before, we have to be careful with the negative and positive sign. And here we have a negative change of energy, negative, to be exact, 57.7 degrees Celsius. So the metal lost temperature or lost energy. Its temperature dropped, and it dropped by negative 57.7 degrees Celsius. Part C says how much heat flowed into the water. And here it says take the specific heat of water to be 4.18 joules per gram per degree. I changed from what the lab manual asked, and I made the specific heat into 4 significant figures, so it's 4.184 joules per gram degree. Okay, first, before we answer this question, let's define what specific heat is. A specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So that means in order for me to take 1 gram of water and change its temperature by 1 degree Celsius, I need to input 4.184 joules of energy into that gram of water. And that will be enough energy to increase the temperature of water by 1 degree Celsius. Okay. Next, well, how much heat flowed into the water? Well, here it seems that the metal was at a very high temperature. So that means the metal contained a lot of thermal energy. Okay, and its temperature decreased to 41.8 degrees Celsius. So all of that energy was not lost. All of that energy that the metal contained at the beginning of the experiment was transferred to the water that was at 23.0 degrees Celsius. And that's why at equilibrium, the temperature of water also increased to 41.8 degrees Celsius. And that increase resulted from the energy being transferred from the hot metal to the water molecules. Okay, so first let's define what Q is. Q is energy. Okay, and energy, here I'm going to call it energy of water, is equal to the mass of water times the specific heat of water times the delta T of water. Okay, so basically Q, which is MC delta T, an easy way, especially for people, pre-med students, to remember it is Q equals MCAT. Okay, so Q is energy, M is mass, C is specific heat, and delta T is change in temperature. Okay. Now, keep in mind, your textbook changed C and made it, instead of C, they're using SH as an abbreviation for specific heat. Now, most textbooks use C for specific heat, not SH, okay? But it won't matter. For our purposes, for this video, we're going to use C because that's the standard specific heat symbol that's used, okay? So, we're calculating the heat that flowed into the water. So here we're concerned with the mass of water, and the mass of water is 49.73 grams. So this is 49.73 grams times the specific heat of water, which is 4.184. I'm going to use 4 significant figures. Gram degree, okay, times delta T. Delta T of water we already calculated in part A, which was positive 18.8 degrees Celsius. Now, if you look, you'll see that with this, we will be able to get our energy, or our Q, in joules, because the grams here cancel, degrees Celsius cancel, and the only unit that's left is joules. So if we calculate, okay, we will get, okay, and I'm going to round, I'm going to keep 3 significant figures only because my temperature here is only 3 significant figures. So the answer will be 3.91 times 10 to the 3 joules. Now keep in mind this is here positive value. They all have positive value, so this is a positive energy. So that means water is going to absorb energy and is going to absorb a positive 3.91 times 10 to the 3 joules of energy. Part D states, calculate the specific heat of the metal using equation number 3. Now before we look at equation number 3, we should really look at equation number 2 as well. Equation number 2 in your introduction states that Q of water is equal to negative Q of metal. That means all of the thermal energy that was contained in the metal was transferred to water. This is the reason why the temperature of the metal decreased from 99.5 to 41.8 degrees, and the temperature of water increased from 23.0 degrees Celsius to 41.8 degrees Celsius. Okay, we already calculated the amount of energy of water in part C, and because we calculated already, we already know what Q of the metal is. So Q of the metal is simply negative Q of water. Now, we already have a positive value for the amount of energy that was absorbed by water, and now we're going to give it a negative energy. So the amount of energy that the metal lost is equal in magnitude to the amount of energy that water gained, but opposite in direction. Okay, so because I already know what Q of the metal is, now I could calculate the specific heat of the metal because I have all the other information in the problem. So Q of metal is equal to the mass of the metal times the specific heat of the metal times change in temperature of the metal. The mass of the metal is right here. It's 147.90 grams. We don't know what the specific heat of the metal is, so I'm just going to keep this SC of the metal. We already calculated the delta T of the metal, and we calculated that in part B of this question, and this was a negative value. It was negative 57.7 degrees Celsius. And because I already know what Q of the water is, I know what Q of the metal. It's the same in magnitude, but opposite in direction, so it's negative 3.91 times 10 to the 3 joules. And now I could calculate, rearrange my equation, and calculate for the specific heat of the metal, and that will be negative 3.91 times 10 to the 3 joules divide by the mass of the metal and the change in temperature of the metal. Now notice that here the negative cancels. So I will obtain a positive value. My units don't cancel. So once I punch in my numbers into my calculator, I'm going to keep 3 significant figures. So here I will get a positive, because all specific heats values are positive, 0.458. The top unit is joules, the bottom units are gram, degree, and those are the units for specific heat. Remember, specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So the answer will be 0.458, and the units are already placed here for me. Part E states, what is the approximate molar mass of the metal? And here it says use equation number 4. So if we look at equation number 4, that's the law of Dulong and Petit law. And Dulong and Petit, they discovered that metals require 25 joules of energy to raise the temperature of 1 mole of metal by 1 degree Celsius. Okay, and this happened to a lot of metals. So here, this is an approximation law where we could approximate the molar mass of a metal if we know its specific heat. Okay, so the law simply says that the molar mass of a metal will equal 25 joules. This is the amount of energy that they found 1 mole requires to raise its temperature by 1 degree. Divide by the specific heat of the metal. And remember, the units for specific heat is joules per gram degree. Okay, so to answer this, I need the answer from part D, which is the specific heat of the metal, okay, which is 0.458 joules per gram degree, and we will answer this by dividing 25.0 joules mole degree divide by the specific heat from part D, which is 0.458 joules gram per degree. Okay, now if we look at the units, we will see that joules cancels. We see that degrees Celsius also cancels, and the units that are left are moles and grams. But if we look here, the moles are in the numerator, but they're per, so automatically they will go on the bottom, and grams are in the denominator, but they're also per, so they will go on top. And these are the units for molar mass, okay, grams per mole. Now your book had an error where here they only gave you the units as grams, but I corrected it. It should be grams per mole. Now we could do the calculation, and we are limited again to 3 significant figures, so the answer will be 54.6 grams per mole. So from this answer, we can approximate what kind of metal it is. Now it's not an exact science, because again it's an approximation, and we will get several metals that could fall into that range. Question number 2. Question number 2 states, when 4.98 grams of sodium hydroxide were dissolved in 49.72 grams of water in a calorimeter at 23.7 degrees Celsius, the temperature of the solution went up to 50.1 degrees Celsius. Before we look at question number 1, which has several parts, and this is very similar to part B of the lab report, heat of reaction, okay, we need to look at a couple of things. Here we're going to be dissolving an unknown solid. And when we dissolve an unknown solid in water, 2 different processes can occur. We could have an exothermic process or an endothermic process. Now, when an exothermic process occurs, exothermic means they release energy to the surrounding. So if I take a solid and I dissolve it in water and it has an exothermic process, it's going to release energy to the surrounding. That energy will be absorbed by the surrounding molecules of water, and will indicate a higher temperature of water. The temperature of water will increase. If we have an endothermic process, the opposite will occur. An endothermic process will require energy. It will obtain that energy from the surrounding water molecules, and therefore the temperature of water will decrease. So we could monitor and define an endothermic and an exothermic process by really monitoring the temperature of the surrounding, the temperature of water molecules. So here, it's the first question says, is this solution reaction exothermic and why? Well, first we got to look at the water temperature. The water temperature for water started at 23.7 degrees Celsius and it increased to 50.1 degrees Celsius. So here it seems that water molecules gained energy, and it gained this energy from dissolving sodium hydroxide. Therefore, this is an exothermic process. So the answer is yes, it is an exothermic process. Why? Well, we just stated it. Okay, the reason why is the system temperature increased, indicating that dissolving sodium hydroxide released energy into the system which was absorbed by water molecules. Part B asks to calculate Q of water using equation 1. So this is very similar to what we did in question number 1. Okay, and if you guys remember, okay, Q of water is equal to the mass of water times the specific heat of water times the change in temperature for water. Okay, so if we look, the mass of water here is 49.72 grams. The specific heat of water, well, that's a constant, so this is 4.184 joules per gram degree, and this is a value that you should memorize. Delta T of water, well, delta T is always the final temperature minus the initial, so here is my final temperature. Here is my initial temperature. Remember, it's an exothermic process, so the temperature of water increased, so this will be 50.1 degrees Celsius minus 23.7 degrees Celsius. Okay, if we calculate, this will be 49.72 grams times 4.184 joules per gram degree, and the temperature will give me a value of 26.4 degrees Celsius, and it's a positive value. Okay, so here I have everything is positive. The mass, of course, is positive. My specific heat of water is positive. My change in temperature is positive. So I will have a positive value for Q, and if I calculate everything and punch the numbers into my calculator, I will get a value of 5.49 times 10 to the 3 joules. And of course, I'm keeping 3 significant figures because I'm limited on the temperature to three significant figures. So the answer here, I already have the units written as joules, so it'll be positive 5.49 times 10 to the 3 joules. Part C. Find delta H for the reaction as it occurred in the calorimeter. I'll use equation number 5. Before looking at equation number 5, let's define what delta H is. Delta H is the change in enthalpy. Okay, and change in enthalpy is the amount of heat or amount of energy that flows in or out of a reaction, depending if the reaction is exothermic or endothermic. Okay, now we already determined that this process is an exothermic reaction, and it's exothermic because the temperature of water increased. Okay, we already calculated how much energy water absorbed in part B. Now, equation 5 states that Q of the reaction, okay, or the amount of energy of the reaction, is equal to the change in enthalpy of the reaction, delta H of the reaction. And that's equal to negative Q of water. Very similar to the first question or the first part of the experiment. Okay? Now we already calculated what Q of water was, and we got a positive value for Q of water in part B, and that was positive 5.49 times 10 to the 3 joules. So delta H for this reaction will simply equal to negative Q of water. So we'll have the same exact amount of joules, but opposite in sign. Okay, it'll be the same exact magnitude, but opposite in direction. So I will have a negative 5.49 times 10 to the 3 joules. So this is the answer for part C, negative 5.49 times 10 to the 3 joules. Okay, now let's look at what delta H will look like in both endothermic and exothermic. So let's draw a table right here. Okay, and we're going to look at a couple of things. First, we're going to look at delta H. We'll look at Q of water. Okay, so let's look at first what delta H would look like, what Q of water would look like, and we'll also look at water temperature. Okay, so if we have an exothermic process like we have in this problem, we'll see that delta H will be negative, will have a negative value. Okay, and that's what we obtained in part C of this problem. We have right here a negative value for delta H. Q of water had a positive value, and the temperature of water will increase. If we have an endothermic process, okay, delta H will be positive, Q of water will be negative, and here we'll notice that the temperature of water will decrease. Okay, now why is that? Well, because in an exothermic reaction, heat is given off. Well, where is that heat, or where is that energy going to go? Well, that's going to go to the water molecules. Therefore, water molecules their energy will increase. They will absorb energy. That's why here Q of water is positive. And because they absorb energy, their temperature will increase. We'll notice an increase in temperature. Where in an endothermic process or an endothermic reaction, energy is required. Energy is absorbed. Okay, so we'll notice that Q of water, okay, will be negative because water molecules will give off their energy to the reaction because the reaction needs energy. It's endothermic. So the value of Q will be negative, And because water is losing energy, its temperature will decrease. Okay? And if we have a positive Q for exothermic, then delta H will be negative. And if we have a negative Q for endothermic, then delta H will be positive. Part D. Find delta H for the solution of 1.00 gram of sodium hydroxide in water. Now, part D is very similar to part C. In part C, we calculated the change in enthalpy, delta H, for 4.98 grams of sodium hydroxide. In part D, it's asking to calculate delta H for 1 gram of sodium hydroxide. Well, the total amount of change of an enthalpy, delta H, from part C was negative 5.49 times 10 to the 3 joules. This amount was for 4.98 grams of sodium hydroxide. So if we take the change in enthalpy from C divided by the mass of sodium hydroxide that this energy was produced from or was given off from, okay, we will get units of joules per gram. Okay, and this will give us a value of negative 1.10 times 10 to the 3 joules of energy per gram of sodium hydroxide. Now, the question is asking us for units of kilojoules per gram. So this here, we would need to convert from joules to kilojoules. Okay, and that conversion can easily be done as negative 1.10 times 10 to the 3 joules per gram of sodium hydroxide. I want to cancel joules, so I will put joules on the bottom. I want kilojoules, so I'll put kilojoules on top. 1 kilojoule is 1,000 joules. And now we could look and see that the unit joules cancels. And the final answer will be negative 1.10 kilojoules per gram of sodium hydroxide. So the final answer here in kilojoules per gram will be negative 1.10 kilojoules per gram. Part E. Find delta H for the solution of 1 mole of sodium hydroxide in water. This is a continuation from part D, where we found the delta H of the solution of 1 gram of sodium hydroxide. So what we have to do is take the answer that we obtained in part D and convert it from change in enthalpy of kilojoules per gram of sodium hydroxide to kilojoules per mole of sodium hydroxide. And in order to do that, what we need to do is say the change in enthalpy, delta H, it was in part D, negative 1.10 kilojoules per gram of sodium hydroxide. And now I want to convert the numerator from gram of sodium hydroxide to moles of sodium hydroxide as the problem states. So I need to know the relationship between grams and moles. Well, the relationship between grams and moles lies in the molecular weight or the molar mass of the substance. And here I need to find out what the molar mass of sodium hydroxide is. So I need to look up the value for sodium, for oxygen, and for hydrogen in the periodic table, add them up, and I find that the molar mass of sodium hydroxide is 40.0 grams per mole. That means every mole of sodium hydroxide has 40 grams of sodium hydroxide. So now I could do the conversion and say 1 mole of sodium hydroxide is equal to 40.0 grams of sodium hydroxide. Now I put grams of sodium hydroxide on top, okay, so I could cancel the original units that I had here, okay, and if we change the color, okay, you'll see that grams of sodium hydroxide had to go on top and moles on the bottom, so this way I could cancel the grams of sodium hydroxide, and my final units will be kilojoules per mole of sodium hydroxide, and if I do the math, it's going to be negative 44.0 kilojoules per mole of sodium hydroxide. So the final answer is negative 44.0 kilojoules per mole. Part F. Given that sodium hydroxide exists as sodium plus and hydroxide minus ions in solution, write the equation for the reaction that occurs when sodium hydroxide is dissolved in water. Okay, so here basically they just want what the chemical reaction will be when solid sodium hydroxide dissolves in water. Okay, so if we look at it, okay, the reaction will be solid sodium hydroxide in water will dissolve into sodium ions and hydroxide ions. And notice here that every mole of sodium hydroxide solid will produce 1 mole of sodium ions and 1 mole of hydroxide ions. This is a balanced equation. All of the coefficients are 1-to-1 ratios. 1 mole of sodium hydroxide solid will dissolve into 1 mole of sodium ions and 1 mole of hydroxide ions. Part G. Given the following heats of formation, delta H of F in kilojoule per mole, as obtained from a table of delta H of F data, calculate delta H for the reaction in part F. Compare your answer with the results you obtain in part E. Here we are given the values of the heats of formations in kilojoules per mole. So sodium hydroxide solid has delta H of F of negative 425.6 kilojoules per mole. Sodium ions has a delta H of F of negative 240.1 kilojoule per mole, and hydroxide ions has a delta H of F of negative 230 kilojoules per mole. Okay, we need to calculate delta H of the reaction for part F. In part F, we already saw that when sodium hydroxide solid dissolves in water, it gives off 1 mole of sodium ions and 1 mole of hydroxide ions. So let's write this reaction down. 1 mole of sodium hydroxide solid. When it's dissolved in water, it produces 1 mole of sodium ions and 1 mole of hydroxide ions. Now that we have what their delta H of F heats of formation for each one, let's write their heats of formation underneath the equation. So sodium hydroxide has negative 425.6 kilojoules per mole of sodium hydroxide. Sodium ions has negative 240.1 kilojoules per mole of sodium ions, and hydroxide is negative 230.0 kilojoules per mole. Okay, so these are all the delta H of formations for the species in this reaction. Okay, now we're asked to find what the delta H for the reaction is. Well, delta H for the reaction is equal to the sum of the chain delta H of formation for all the products minus the sum of all the delta H of formation of the reactants. Okay. Now here I have two products. I have 1 mole of sodium ions and 1 mole of hydroxide ions, and in the reactant I have 1 mole of sodium hydroxide solid. Okay, now let's look at the products first. Okay, so 1 mole of sodium ions, if I multiply it by its delta H of formation, okay, I will obtain the amount of energy that sodium ions have, or its delta H of F, which will be negative 240.1 kilojoules. Okay, because that's how much each ion, its delta H of formation is negative 240.1 kilojoules per mole. So 1 mole will have negative 240.1 kilojoules. The next product is hydroxide. I have 1 mole of hydroxide. Hydroxide has a delta H of F of negative 230.0 kilojoule per mole. So this here also will be negative 230.0 kilojoules, because that's all I have is just 1 mole of it. And to subtract that from the reactants, well, I only have one reactant, that's sodium hydroxide solid, and I have 1 mole of it, and the H of F, delta H of F of sodium hydroxide solid is negative 425.6 kilojoule per mole. So this here will give me a value of negative 425.6 kilojoules. Okay. Now I will calculate the products first because I have two products, and if I do that I get a value of negative 470.1 kilojoules. And now I could subtract this from the reactants, which is negative 425.6 kilojoules. I do the final calculation and I find that the delta H of the reaction is negative 44.5 kilojoules. Okay. Now this amount of enthalpy of the reaction is coming from 1 mole of sodium hydroxide. Okay, here in the reaction we calculated this according to 1 mole of sodium hydroxide. So here, when it's asking for the enthalpy, change in enthalpy per mole of sodium hydroxide, this is the amount given off by per mole of sodium hydroxide. So the answer is negative 44.5 kilojoules per mole. Now this here is the literature value, because it's coming, these values that I used here are coming from a table of delta H of F, or the enthalpy or the heats of formation table. Okay, now the problem here asks us to compare this to the results that we obtained experimentally, and experimentally we calculated the experimental value in part E, and in part E we obtained that the value was negative 44.0 kilojoules per mole. So experimentally, negative 44.0 kilojoule per mole. According to the literature value, we should obtain negative 44.5 kilojoules per mole. So here it seems that they agree very reasonably Okay, so here I would say the results of part E and G agree very well. There is, of course, experimental error, but they agree very well. One is literature value, negative 44.5 kilojoule per mole. Experimentally, I obtained negative 44.0 kilojoule per mole.